Hello, everybody. We are the Automatic Georeferencing for UAV video team. We are sponsored by Parkalytics, and we'd like to give a quick thank you to our industry mentors and faculty mentors for helping us the past 2 quarters to accomplish our project. We'd first like to start with our problem statement, which is to detect vehicles and calculate pose data from UAV video and superimpose video and analysis on satellite imagery taken for potentially different times and seasons. Our objectives can be split into two main groups, which is our georeferencing team and our object detection and tracking team. Our georeferencing team's goals are to estimate projection from video to satellite imagery, identify basic ground control points between frames, and use geographic metadata to calculate pixel locations in real-world coordinates. Our object detection and tracking team goals are to detect and classify common roadway objects from UAV videos, such as cars, trucks, bicycles, humans, vans, etc., and to track roadway objects under varying conditions, including lighting, and occlusion. Finally, our last goal is to improve new model performance compared to the current model, which is Waldo, which is currently employed by Parkalytics. Combined, these two teams should estimate all vehicle positions and velocities, display visual analysis of data, such as heat maps and vehicle tracks. Here's a quick design chart of our project. On the left, we have our georeferencing team, and on the right, we have our object detection and tracking team.
Diving into the specifics of our implementation, I will begin by talking about our georeferencing process and output. For image registration, we decided to use superpoints and superglue, a convolution neural network developed by other students and made open source on GitHub to detect and match features in outdoor images. A CNN is the ideal choice because a large set of linear parameters can be fitted to nonlinear data, as is required to accurately match key points between images in different settings. In this example, called 207, a large shadow and a missing building may throw off a linear matcher. In another example, called 215, we see an intersection in the winter from an angled perspective and the same intersection in the summer from an overhead perspective. However, CNNs are generally not rotation invariant, so we made a small concession and ran the algorithm for 6 sets of rotations of the input satellite image, which is always an overhead shot. The performance impact on our benchmark hardware is less than 2 seconds. For video stabilization, we set the 0th frame as our base frame and used orb and flan to map all successive frames to the base frame. This approach assumes the drone stays near its original recording point. We rely on parked vehicles, as well as building and road features to act as control for moving vehicles. By mapping within the video and not to the satellite image, our program can process about 10 frames per second.
To transform the pixel coordinates of the input video to their real-world coordinates, we want to extract the affine transformation from the generative metadata, which is included as one of our input resources. From this, we can georeference the video and later on transform the pixel coordinates of the bounding box to real-world coordinates. As a result, here we have two datasets, 212 and 215. Both have their UAV videos overlaid on the satellite image, and at the end, we also produce a frame-by-frame transformation matrix.
I'm going to share our work on development and training object detection models. In the realm of object detection, speed and accuracy are both important. YOLO models are known for their rapid processing times without significantly compromising accuracy, so we chose YOLO models. We picked 3 types of YOLO models: YOLO V9, YOLO V8, and PPYOLO-E FOD. We wanted to see which one works best on our videos. First, we tested these models on our videos using Cuckoo pre-trained weights. However, the results weren't as good as we hoped, as shown on the left side. Since the Cuckoo dataset doesn't include aerial perspectives, we needed more specific training. To improve, we used a large join dataset called Withjoin, which has many aerial photos similar to our videos. After training on Withjoin, the results were much better, as shown on the right side. We chose the track-by-detection method over an end-to-end model for object tracking due to its flexibility and robustness. Tracking by detection consists of a detector and a tracker. This method allows us to optimize and fine-tune each component independently, enhancing performance for challenging tasks. It's also more resilient in tough environments. For instance, in UAV videos and severe weather, even if detection quality drops, a well-trained tracking algorithm can still associate objects correctly, while an untrained model might fail. In our system, we use UV8 for detection and by-track for tracking. This combination has performed well in our tests.
Next, we will go over the detection results for the Waldo model compared against the ground truth data. On the left, we have a frame of the ground truth data. In this frame, there are 67 cars, 3 humans, and 3 trucks. On the right, we have the output of running this frame on our Waldo model. As we can see, the Waldo model detects 58 cars, 0 humans, and 0 trucks. This is an example of how the Waldo model is lacking. It doesn't detect a lot of most of the cars, it doesn't detect any humans, and it doesn't detect any of the trucks. Next, we will compare the same ground truth frame on running it on our PP YOLO V8 model. On the left again, we see our ground truth frame, 67 cars, 3 humans, 3 trucks. On the right, we see the output of running this frame on our model, 67 cars, 0 humans, 2 trucks. This is an improvement from the Waldo model. As we can see, it detects all the cars, it has trouble detecting the humans, and it has a great improvement in detecting the trucks as well.
To further improve the performance and robustness of our models, we attempted data augmentation and increasing input image resolution to 960 square or 1024 square pixels. We generated an augmented dataset from our original mixed datasets from the Visual dataset and the sponsor-provided videos. The augmentation include horizontal flip, random rotation, random shear, and salt and paper noise, which was applied to 0.77% of noise. And the result of both attempts suggests further efforts. For 1024 square pixels input, our 2080 Ti GPU encounters out of GPU memory error, even with batch size 1 during training. And for 960 times 960 input, no significant improvement was observed for both YOLO V9 and YOLO V8 series models. For data augmentation, models trained with augmented data has lower performance than the model trained with original dataset. For example, the YOLO V9 trained with augmented datasets has lower performance or lower MAP, that is mean average precision, than the YOLO V9 trained with original dataset. Therefore, both attempts require further improvements with better GPU and better augmentation configurations.
Okay, so here I'm gonna talk about the performance of different models. Here the most important parameter is the MAP, mean average precision, which is calculated by true positive divided by the sum of true positive and false positive. So all data set except the Waldo are trained on mixed data set of Visual and a Video 207 from our industrial sponsor, and they're all tested on Video 212. So here we can see the Waldo model that we originally used has the parameter size of 36.6 million, and the mean average precision is 0.423, and with the speed like frame per second of 30. So the PPLOE is bigger than that and has a higher mean average precision, but FPS is way slower. So the YOLO V8X, this the model we actually use, is the biggest model among all these, and it has the highest mean average precision. So the reason why we don't use YOLO V9E is because it has a slightly lower mean average precision here, even though the speed is is a little bit faster than the V8X. But since we're doing all the video processing like not in real time, like we process in the backend, so the time is not really a big concern for us. So here we got the YOLO V9E with the augmented dataset. It's about the same size as the YOLO V9E, but the mean average precision is way lower than that. I guess it's because we didn't do the data augmentation on the tested data sets, so that's what makes the mean average precision way lower.
Now let me demonstrate our final product. This is a video shot by a drone near UW, and let me show you how we are going to use our final product. And this is the script to use the final product. The argument here, these two arguments are the source files of the video and the georeferencing background image, and this flag asks the system to generate an output visualization of the georeferencing output. And those two arguments specify the frame we want to process in the video. And this is the application that is the top module we have to run this our models. And here are the codes to implement the detection and object tracking. And you can see the YOLO models here. Okay, the model finished running. Let us check the results. And this is output video, and we can see that the green number are the tracking IDs, the red numbers are the type of the detected object, and the blue numbers are velocity in meters per second.
Our program outputs 3 final products. The first is a video that contains the original video mapped onto a still of the target satellite image. We annotate each detected object with its tracking ID in green, its object class in red, and its speed in cyan. This is just a visual aid to confirm all of the calculations in the code are accurate and reasonable. The second is a frame-by-frame transformation matrix that can be used on the source video directly in the event a different detection and tracking algorithm is preferred. The third is a heat map of vehicle speeds in the video, a sort of cherry on top for the previous major outputs. We return to our problem statement to close our demo. Our work successfully achieves the goals in our problem statement. We are able to detect, track, and calculate trajectories of vehicles in a video. We are able to transform that position data from pixel coordinates to real-world coordinates through GeoTIFF metadata. Lastly, we are able to overlay our results on the provided satellite imagery as a visual confirmation of our results. Thank you for your time in watching this video about our Capstone Group's presentation, Automatic Georeferencing for UAV Video.